Hi, welcome to this lecture on mathematical methods for biologists. We have been learning about vectors, how to represent quantities having certain direction. So now we will learn more things about vectors and how to apply this for some context in biology. So the topic of today's lecture is gradient, forces and flows. Gradient, forces and flows, how to mathematically represent forces and flows, that is currents, as derivatives of a scalar. So this is the question that we will answer in this lecture, how to mathematically represent forces and flows. Flows, by flows I mean currents, which I will explain, as derivatives of a scalar. Typically these forces and flows are derivatives of a scalar, and we will see how this comes. So the first thing we would know, so of course we know that scalar is a quantity which is as a magnitude and no particular direction, and the examples of scalars are, so something that we know, scalars are like concentration and energy. These are some examples of scalars. For example, two examples of scalars are concentration and energy. Now, if you think of concentration in a cell, what would come to one's mind? Like, so let us think of something, concentration in a cell, or so let us take first a very thin one-dimensional cell, like a cell which would look like, let's say, looks like a very thin line like this, a thin line like this. So essentially like a one dimension. Now if you think of concentration here, let us say there is very high concentration of something here and very small concentration of something here. I will draw this big for the purpose of description. So for the purpose of description, let me draw this big. So we have essentially a one-dimensional along the line, which I would call x, along x. So this is x equal to 0 and this is x equal to L. So along this, there is a very long thin line. Now if you think of concentration of a particular protein in this kind of a cell, let us assume that there is large concentration here, and as we go along, there is lesser and less concentration. Like, so this is, imagine a concentration like this. So high concentration here, so let us say this is 10 micromolar is the concentration here, micromolar. So I should write here concentration is 10 micromolar. Here at this end, let us say it's like essentially 1 micromolar, and the length, let us say here this is in microns, so this is 0 micron, and here let us say this is some particular amount of micron, 10 micron, micrometer. So this is the length, x equal to L, which is 10 micrometer. So you have a 10 micrometer long thin tube, which is like if you imagine cell like a thin tube like this, and you have gradient of concentration which is from micromolar to 10 micromolar to 1 micromolar. So such things are called concentration gradients. Concentration gradient. What does that mean? It means that concentration is changing in space. Concentration varies in space. Concentration varies in space. So this spatial variation of concentration, that is high concentration here, and as I go along the space I have low concentration here. So this spatial variation of concentration from one part of the cell to the other part is concentration gradient, and how do we mathematically represent this? This is the question that we will first discuss. So to mathematically represent a concentration gradient, so I have to first so if C as a function of x is a concentration along this, there's a high concentration here and low concentration as we go along. So this is the concentration gradient C of x. Now as I move, so this is 10 micromolar here, and let us say I go by 1 micrometer, and this is like 0 micrometer, 0 micrometer is the distance. As I go 1 micrometers, as I move here, and the concentration is 9 micromolar. And as I go here, let us say the concentration is 8 micromolar, and so on and so forth, and it will become like 1 micromolar here. So the concentration is changing 1 micromolar every micrometer. So this is 1 micrometer, the distance here, this is 0 micrometer position, and here it is like 1 micrometer is the distance, and here it is 2 micrometer is the distance, and as I go along, the concentration is changing. So delta C, the concentration is changing as I go along the distance x. So as I go along x, the concentration is changing, and this is, let us say, about 1 micromolar per every micrometer. So this is the change in concentration, and this change in concentration, when I take very small delta x, I can write this as del C by del x, where, or since this is del here is a partial derivative, which means the concentration is varying only with respect to x and not with respect to y, z, or t or anything. So this is only with respect to x, this is what it means. Here, since we have nothing else, this could also can be written as dc by dx. So I would use dc by dx here. There is no, I neglect time and other things and only assume that it is changing along x and only the variable is x. Therefore, this is dc by dx. So the concentration here is the dc by dx is the change in concentration, and this we know to mathematically represent the change in concentration as a derivative dc by dx. As I go along x, the concentration changes. So that is what this dc by dx means. Now, it turns out that this change is along the x direction. Like if you take now this two-dimensional thing, like if you take x and y, this change can happen in y or along the x and along the y. Even in the one direction, it could increase along the positive x or increase along the negative x. So let us contrast two things. Let us contrast two things. So first thing is, so let us draw two boxes, and if you have high concentration here, so here it is 10 micromolar here, 10 micromolar here, and 1 micromolar here. And let us think of the opposite here, which is very high concentration here, and as I go along, little here. So here, this is 10 micromolar and 1 micromolar. Now, in these two scenarios, so this is my x-axis, x direction. So this is x equal to 0, and here x equal to 10 in units of micrometer. So this is my increasing direction of x. So here as x increases, the concentration increases. Here as x increases, the concentration decreases. So as x increases, here as x increases, the concentration decreases, dc by dx, and here as x increases, the concentration would increase. So dc by dx will have different sign. So now when I would say this, one can, to represent this and this differently, one would want to have a vector sign. Here the concentration is increasing this way, while here the concentration is increasing this way. So to represent this mathematically, one could write dc by dx x cap. This would mean that the concentration is changing along the x direction, and the dc by dx sign would tell this is positive or negative. So this symbol, this x cap would tell us that the change is happening along the x axis. Now you could have a situation where the change is happening along the y axis. So to represent that, we would do it differently. So this, if I just write dc by dx x cap, so this is gradient of, see, this is a vector, this has a direction, it is changing in a particular direction along the x axis. Therefore del c by del x x cap would mean that gradient of c, and it has the direction along the x cap, and it could be minus x cap or plus x cap depending on a sign. If I put a negative sign, it could have the opposite sign. So this would, to represent that it is changing along the x axis, I would use dc by dx x cap, and therefore this has a particular direction, therefore this gradient is like a vector. Let us understand this a little bit more carefully by taking x and y. So let us take x and y. So this is like more like x and y, and let us say the concentration is changing only along the x axis. So it is, let us say, same concentration everywhere here, and next trip the concentration is reduced a little bit, and the next trip the concentration is reduced further, and the next trip it is reduced further. Here the concentration is further reduced, here the concentration is 0. So this would tell us that the concentration is kind of independent of y. Everywhere you take, for all y value, the concentration is same. So let us say the concentration here is minus kx. As the x increases, the concentration decreases. So let us say the concentration, so let me write an equation for concentration. C of x is equal to 10 minus x in micromolar. This is the concentration. So that means x is equal to 0, it is 10 micromolar. When x is equal to 1, it is 9 micromolar. When x is equal to 2, it is 8 micromolar, and so on and so forth. So this is the formula for the concentration. Along this I would write. Now the fact that the change in concentration happens only along x, so would mean that the dc by del c by del x x cap would mean that the concentration varies only along x axis and not along y axis, or this represents the change in concentration along x axis. Del c by del x x cap would represent the change in concentration along y axis. So this, in this case, would be derivative of 10 is 0, derivative of x is minus 1, so minus 1 x cap. The answer is going to be minus 1 x cap. So, and the unit del c by del x would be micromolar per, let us say, micrometer. Micromolar per micrometer. This is typically a unit like this would emerge. So this would mean that the concentration is changing along the x-axis minus 1 the change in concentration is -1 micromolar per micrometer as we go along the x-axis like this. Now let us think of concentration changing both along the x-axis and y-axis. So if you think of a real cell, if I just draw an x-axis and a y-axis and draw a real cell like this, some real cell like this, and the concentration here could change both along x and y. There could be very high concentration below here and low concentration as we go up and as we go along the right. So as I go along the x-axis, the concentration is decreasing. As I go along the y-axis, concentration is also decreasing. So the change in concentration along the x-axis can be written as del C by del x along x cap, and the change in concentration along y-axis can be written as del C by del x along y cap. So these two things combined together, I could write del C by del x, which is the concentration change along x cap, plus concentration change along y cap, which is del C by del y along y cap. This together, if I do calculate this, this will be a number. If I calculate this, will be another number. Together this, there will be some vector which is called the gradient vector. Let me call it G at the moment. It is the gradient vector. So the gradient vector G can be written as some derivative. This would give us a number times x cap plus some other number times y cap, and this is the x changing along x axis and change along y axis for any given x. So this is, I take a y value, and so that is my y value here, and I study the change along x, and this would give you, keep the y constant, and what is the change along x? This is what this will give you. Take another y value. For a given y value, what is the change along x is given by this del C by del x. This is partial derivative, therefore y is a constant. For a given y value, the change along x, how the concentration is changing along this line. How the concentration is changing along this line. That's what this gives. This gives, for a given x value, how does the concentration change along the y axis. So here, this would give us, for given a x value, how is the concentration changing as I go along this line. So keep this x value, I go along this line, how is the concentration changing is del C by del y, and the direction is y cap. Similarly, take any other x line, so this is x equal to some constant, and if as I go along the line, how does the concentration changes, that is del C by del y. This is a partial derivative, that means x is a constant, only change along y is measured. This is what the meaning of the partial derivative, and this would give us the overall change in this two dimension. So that vector is the gradient vector. Now there is a way to represent the gradient mathematically. There is a symbol. So the symbol typically is written as this way. The gradient of concentration is, the gradient G is typically written by this symbol del C, which would mean gradient of concentration. What is the definition of del C? In two dimension, del C is del C by del x along x cap plus del C by del y along y cap. So this is the definition of this. So as we know, del C by del x will give us a number, and this will also give us a number, and along x this is the change, along y this is the change, and this is the gradient in two dimension. Similarly, we could have the gradient of course in three dimension. if in reality everything will be in 3 dimension. Del C in 3 dimension is del C by del X along X cap plus del C by del Y along Y cap plus del C by del Z along Z cap. So this symbol means gradient. So grad is also written as gradient. So gradient of concentration, grad C. This can also be written as grad C. This is also has a meaning grad C. So gradient of concentration, grad C, is equal to del C by del X, X cap plus del C by del Y, Y cap in 2D, in 2D, 2 dimension. In 3 dimension, del C is del C by del X along X cap, del C by del Y along Y cap, del C by del Z along the Z cap, which is the Z axis. So along X axis this is the component, along Y axis this is the component, along Z axis this is the component. So this is 3 components. I could write this is a number, this is another number, this is another number. These 3 components together will form this vector del C. Now, of course, as we said, this has the dimension of concentration by in space, right? In per length. So, like change in concentration per unit length. So that is the dimension of this quantity. Now it turns out that in biology, proteins diffuse one part to the other, and the fundamental idea of diffusion is that one would naively understand diffusion as flow of proteins from higher concentration to lower concentration. So there is a current or a flow of concentration or protein molecules, then they will flow from higher concentration region to lower concentration region. Now it turns out that how much is this flow? If you want to quantify this flow, one needs to understand this idea of gradient. So the question we have is that, the question that is biologically one need to pause and ask is that, imagine that you have a concentration gradient like this, where you have, as we were discussing, high concentration here and low concentration here. So here it is very high concentration, let us say 10 micromolar to 1 micromolar, and this is the distance is x, which is 0 micrometer to 10 micrometer. So as I go along the x, the concentration changes, and it turns out that the flow, how much, the question we have to ask is, how much will be the flow or diffusive flow? How much will be the diffusive flow in this case? Diffusive flow or a current. This is the question that we want to answer. How much will be the diffusive flow given that there is 0 micromolar here and 10 micromolar here and 1 micromolar here along this gradient of 10 micrometer. It turns out that this answer to this question is that the flow is J is proportional to the gradient of concentration. J is proportional to gradient of concentration, and it turns out that it can be written that J is equal to some constant called the diffusion constant times the gradient of C. So the J is a vector. The vector is proportional to del C, which is something we learned, and this is exactly equal to some constant D, which depends on the property of the medium and the particles, size of the protein, and so on and so forth, which we will learn what is this D. But once we know the d, which is the property of the system, which is the property of the medium, molecule and all that, the flow is given by J is equal to d del C. So we will understand this a little bit more in detail, and it turns out that this is also true for forces, and we will come and learn this a little bit more carefully, that how the forces also is like a gradient and how one can understand this force as a gradient. So let us just quickly state this, that the force can also be written as gradient of energy. So there is one thing which break. I want to do, there is a mistake. I want to repeat. So J is proportional to minus del C, and J is proportional to del C, and this, it turns out that this is minus d del C. J is equal to minus d del C. So this actual flow or current is d del C with a negative sign. So we will learn about this in detail soon. We will understand this, how, why, what is the meaning of this. But the answer to this question, that how much will be the diffusive flow or current, it turns out that it is J minus d del C. In other words, let me rewrite this a little bit more carefully. Diffusive flow is J, which is a vector, which is minus d del C. How much will it flow given a concentration gradient? This is the amount it will flow, where d depends on the property of the medium and the material proteins that we study. And we will calculate d. D was famously calculated by Einstein in 1905, and we will discuss about this in the coming lectures. This, if I expand, I would get minus d times del C by del x along x axis plus del C by del y along y cap, and so on and so forth. Let us write in 2D. In 1D, it is just minus d del C by del x x cap. So that is the change in the slope, the change in concentration along the x axis minus d times x cap. This is the flow. This will be the exact amount of flow or current of proteins. We will come back and understand this little bit more in detail soon. With this, we will stop this lecture by summarizing that we learned that the gradient is change in concentration, and which is essentially gradient can be written as del C, grad C, and this gradient is useful in computing, for example, diffusive flow and many other things, including forces, which we will learn in the coming lecture. With this, we will stop this lecture. Bye.